Hello, we are Team 11, RISC-V FPGA-based CPU and programming language, or FISH-V for short. I'm Kyle Prince.
I'm Yahya Al-Shamali.
And I'm Charles Ancheta. We would like to give thanks to our sponsor, Stephen Knudsen, for his support and guidance, alongside the myriad of fish puns.
We started as a compiler project for 11 engineering, but the lack of an operating system for the Zinc 2 processor would make it difficult to run the compiled code. So we decided to pivot. Meet FISH-V.
FISH-V is two projects swimming together in open source harmony. The first of which is a fish-themed programming language called Fish. The second is an FPGA RISC-V CPU that runs Fish programs.
Fish is esoteric at its core. Its goal is to create a fun, educational, and simple-to-use programming language. Every component of the language symbolizes a real-world concept, like fish scales representing their value and tadpoles swimming towards bigger fish.
The second sub-project is an FPGA-based RISC-V CPU. It's designed to be simple and just barely able to run fish programs. It can be used as a learning tool for students and has a custom instruction for random number generation we call grilled fish. It uses the voltage noise from the development board's analog to digital converter to generate a random number.
While this project is not a typical product, it serves as an amalgamation of computer engineering concepts that we have learned throughout the program, such as computer architecture, FPGA design, development tooling, and being thrown into an ocean of work and expected to swim. These skills were essential in developing the FISH-V project.
FISH-V aims to expand these concepts by using industry-standard frameworks such as the RISC-V instruction set architecture, LLVM compiler infrastructure, and language server protocol. It can also serve as a reminder to future computer engineering students that there's no such thing as too much fun.
The outcome of this project is successful end-to-end functionality, taking in a program written in Fish and executing on the FISH-V CPU. However, some features of the language are not quite yet fully supported, such as recursion with tail call optimization, return statements, conditional loops, and arrays.
Let's take a look at a factorial example in Fish. In Fish, all numbers are written in binary. Curly brackets represent 1 and regular brackets represent 0. The fish eye is there purely for aesthetic purposes. Here we have a fish that's equal to 101 in binary, or 5 in decimal. The result is equal to 001 in binary, or 1 in decimal. The fish with a looped eye is a while loop. For the condition, we have a variable named fish, a tadpole, and a fish of value 010, or 1 in decimal. The tadpole represents the greater than symbol as it swims towards the bigger fish. So altogether, its while fish is greater than 1. The body of the loop has two fish multiplying together and stored into the result variable. Heart symbols represent multiplication since, the fish with two tails and swimming to the left is decrementing fish by 1. If it was swimming right, it would have incremented instead. Now let's take on a harder problem involving custom functions or subroutines. This problem is the first morning problem we received in Compute 274 called bed. The problem we're trying to solve is finding the area of a bed given the coordinates of two corners of the bed. To solve this problem, we need to define an absolute value function. To define the subroutine, we need a submarine called abs with a parameter called num. As you can see, our VS Code extension automatically gives us the submarine. Now we need to check if number is greater than 0. If statements are represented by happy fish, while else statements are represented by dead fish. If number is greater than 0, we need to return num as is. The return statement is represented by a baby squid. If num is less than or equal to 0, we return negative num. This is represented by the fish swimming to the left. Now, let's define x1, y1, x2, y2 as 2, 4, 3, and 9. With the help of the language server, this task is a breeze. Let's get the area by subtracting x2 from x1 and y2 from y1 and multiplying the two distances together. We then need to get the absolute value of the area by calling our absolute value submarine. Calling a subroutine involves putting the submarine and its parameters inside of square brackets called the fish tank. Ta-da! Now we have the 2D area the bed would take up.
This is our demo program that makes LED fish swim. Here we have two subroutine definitions. setPixel is for setting GPIO output, and drawFish is for drawing an entire fish. The main program actually calls drawFrame, which is defined in C, which in turn calls drawFish 100 times. Fish really shines when interacting with C. Let's compile this program and flash the firmware to the Fish-5 CPU. This is the build process for the ROM. The fish source code is transformed into LLVM intermediate representation, or LLVM-IR. This IR is passed to the LLVM static compiler and transforms into RISC-V assembly. The assembly from the fish program, along with the other low-level functions for Fish-5 written in C and assembly language, is compiled into object files using Clang. The object files are then built together into an ELF file using a custom linker script. We simply extract the raw binary from the ELF file using LLVM object copy. We then use a custom program called 5ROM to transform the binary into a VHDL package file. This is then imported and synthesized along with other Fish-5 VHDL components. Now let's run the implementation and generate the bit stream. Now we can program the board using the program board tickle script. And we can marvel at the moving fish. Wow.
What we got right. We've successfully got fish programs fully running on the RISC-V CPU. We also have a satisfactory programming language syntax. The Fish-5 CPU also has a fully functioning grilled fish extension. Finally, using LLVM for our compiler felt like the right move, making the RISC-V code generation exponentially easier. What we got wrong. One of our proposed deliverables was a digital aquarium using the 64 by 64 RGB LED matrix, but we did not order it on time. This resulted in us not having enough time to develop a program using the 64 by 64 matrix. We got around this by reusing the 8 by 8 monochromatic LED matrix from ECE 212. We also encountered bugs when creating conditional statements, so early returns also do not work. We got around these bugs by moving fish code with problematic codegen into C functions and then calling those functions in fish.
These compiler bugs stem from one of our bigger mistakes, which was using C++ to write the compiler. Had we used an easier programming language like Go, we would have been able to move faster with our tasks. However, the biggest mistake we had in this project was not printing Fish-5 logo stickers. Having Fish-5 stickers would have boosted the group morale and encouraged us to go above and beyond. Even with this huge setback, we were able to accomplish some extra tasks that bring this project to the next level.
We created a language server called Fish Shells, following the Open Language Server Protocol that is used by many modern text editors and IDEs such as Visual Studio Code, NeoVim, and the JetBrains IDEs. This language server currently only provides syntax highlighting and code completion for fish literals. We also created a VS Code extension that interfaces with fish shells while also providing snippets for some common use cases such as defining functions and using variables. And have you seen our cool poster? It looks even better in real life.
We have a lot of work ahead of us to make Fish inclusive for all. The first step is to make Fish installable on other desktop platforms such as Windows and Mac OS. It shouldn't take a computer engineer to install Fish.
We are also planning to create an interpreter called Babelfish. Writing an interpreter instead of a compiler would speed up the implementation of new fish features. We can also have floating point numbers, strings, arrays, and other data structures without worrying about memory allocation and creating our own standard library. This also allows us to run Fish anywhere, even on the browser, by compiling to WebAssembly.
Another future task would be to make it easier to flash firmware into the Fish-5 CPU. This would involve interfacing with the Zybo board's processing system to load programs either from the flash memory or the SD card. This would significantly speed up development time as changing the firmware would not require a full synthesis of the CPU. Overall, The Fish-5 project accomplished the goal of designing a custom programming language that compiles to RISC-V and executing that program on an FPGA-based RISC-V compliant CPU.
Some significant challenges we faced were implementing functions, developing the demo project, and hardware debugging. Implementing functions is generally a difficult step in compiler design, while the synthesis step for the FPGA introduced difficulties with iterating on the demo project and debugging the CPU.
Altogether, the project was a success, while allowing considerable opportunities for future work such as RISC-V CPU extensions, new language constructs, and cross-compiler support for other target platforms.
In conclusion, it's not just about learning to code or understanding hardware, it's about inspiring a new generation of engineers to think outside of the traditional boxes of computer science and engineering.